Good morning, students. Myself, Vijay Shankar from ECE Department, Chibrol Engineering College. Today, we are going to discuss about the Z transforms. So, actually, this is 5th unit for the secondary ECE students, and this is 6th unit for the triple E students, third year triple E students. Okay. The Z transform. So, already we discussed about the transforms, Fourier transform, Laplace transform. Now it is a Z transform. All transforms doing the same thing, converting the time domain to the frequency domain. X of t to the x of omega as a Fourier transform. X of t as x of s frequency domain by using the Laplace transform. And Fourier series also, x of t by using the Fourier series x of k. All these are converting the time domain function as an input and the response, nothing but output is in the frequency domain. But whatever we discussed previously, the Laplace transform and the Fourier transform is for the analog functions. But coming to the Z transform here is not the analog, it is a discrete time. The another name it is, we're calling it as a discrete time Fourier transform. Okay, so discrete time Fourier transform. The transform is generalization of the discrete time Fourier transform. We learned in the previous, it is a chapter 5, it is here. But here, previously we learned, as we will see, the Z transform allows us to study some system properties that discrete time Fourier transform. See, actually the discrete time Fourier transformation, in the Fourier transformation, what is the definition of the Fourier transformation? The x of omega is equal to integral. What is the definition of Laplace transformation? X of omega is equal to integral minus infinite to infinite and minus infinite to infinite. Taking off the time domain signal in both the cases and multiplying the e power minus j omega t dt. Instead of j omega, we can replace the s, it becomes of Laplace transformation. So before also we learn the exponential Fourier series, the integral minus infinite to infinite or 1 by t, the integral t, the x of t e power minus j k omega naught t dt, j k omega naught t dt. All it is a time domain functions converting into the frequency domain functions. X of omega is a Fourier transformation, x of k is a Fourier series, and the x of s is a Laplace transformation. But coming to the Z transformation, we are not taking the continuous time signal x of t. We are not taking the continuous time signal x of t. Here, the signal is discrete time signal x of n. And the Z transformation definition saying that x of z is equal to, we are not using the integral because it is a continuous time signals, and coming to the Z transformation is a discrete time signals. Sum of n is equal to minus infinite to infinite x of n. Instead of integral, here we are using the sum of, because it is a x of n, the time domain signal, what we are saying here, it is a discrete time signal. And these three are the continuous time signals. X of n and z power minus n. Z power minus n. Whatever here, it is exponential, negative exponential, and here also the negative exponential. And here also the negative exponential is multiplied with the time domain signal. And in this, the time domain, the discrete time signal is multiplied with the z power minus n. This is a transformation definition. The sum of n is equal to minus infinite to infinite x of n z power minus n. Converting of a time domain signal, that too it is a discrete time signal, to the frequency domain signal x of z, nothing but is a digital or discrete, we can say the digital, and these are the analogs. How we can convert the Laplace transformation, the mapping of the Laplace transformation to the Z transformation, mapping of a Laplace transformation to the Z transform. So you'll explain that before that, you go see that what is the definition. It's a transform of discrete time signal. It's a transform of a discrete time signal. X of n is x of z is equal to sum of n is equal to minus infinite to infinite x of n z power minus n. We denoted that Z transform operation is x of n is a Z transform of x of z. What we discussed, we already presenting the x of t Fourier series x of k. The same thing, the x of t, we can take the Fourier transform x of omega. Same thing, the x of t, we can take apply the Laplace transformation x of s. But now it is not the x of t, it is the x of n here, the z transformation. X of n, the z transform, will get x of z. X of z. Now, z is nothing but in terms of the complex number. Z is in general, the z in is a complex number. Therefore, we may write z as z. So x of or the x of x plus iy is a rectangular form. Converting this rectangular form to the polar form. What is the polar form? Magnitude. We'll get the magnitude and the angle. What is the magnitude? We can represent it as r. R is equal to under root of x square, the real term, plus y, the imaginary coefficient y square. And the angle, you can say that's omega r, that's theta, we can say. Theta is equal to tan inverse of imaginary coefficient by the real term, y by x. And this depends upon it is the first quadrant and the second quadrant and third quadrant and the fourth quadrant. The theta will change according to the quadrant values. Okay. And r and the theta, you can represent it in the z as z is equal to r into e power j theta, where r is a magnitude and the theta is a phase angle for the complex function. The complex x plus iy, the rectangular form, is converted to the polar form, representing in the z is equal to r into e power j theta. So, in the definition, you can substitute that theta here they taken as omega. Okay, r e into e power j omega. So, I'm taking the, instead of theta is omega, let us assume j omega. X of z, in the definition saying the x of z, r into e power j omega, let us take, and sum of n is equal to minus infinite to infinite x of n, and z, what is the z here? I'm taking e power minus j omega whole power minus n, replacing the z as r into e power j omega. Now assuming the magnitude is 1, magnitude is equal to 1, magnitude r is equal to 1. Now the equation becomes of x of e power j omega is equal to, I'm substituting the r is equal to 1. See, when r is equal to 1, the equation 1 becomes, is the equation 1. So 0.1 was whatever they're showing here. The equation 1 becomes x of e power j omega is equal to sum of n is equal to minus infinite infinite x of n, and here the r is equal to 1. 1 power anything is a 1 only, and e power minus j omega n. Minus is there and j omega n. Following my distance. Here the right hand side, observe here, is similar to the Fourier transformation, but the time is here the discrete time, which is the discrete time Fourier transformation, the DTFT, discrete time Fourier transform of x of n. Therefore, discrete time Fourier transform is a special case of Z transform. Pictorially, you can view the discrete time Fourier transform as the Z transform evaluated on the unit circle. Evaluated on the unit circle. Why they are saying the evaluated on the unit circle? Because they are taking the r is equal to 1. The radius r is equal to 1, or the magnitude r is equal to 1. Using this, the unit circle. So well known, the 30 IIIE students, they know why it is a unit circle, because they did Bode plots, polar plots, and Nyquist plots. In the polar plots, you will get in the r is equal to 1 is the remaining passes through that negative real axis or the positive real axis, the magnitude or the gain margin and the phase margin will get. Okay, the polar form. And we are taking that is a unit circular. Following my distance. I will explain here. So remember that we choose a discrete time Fourier transform of x of n. Therefore, discrete time Fourier transform is a special case of Z transform. Pictorially, we can view discrete time Fourier transform as Z transform evaluated on the unit circle. Evaluated on the unit circle. We'll explain the mapping here. See, the r is equal to 1. It's a 4 quadrants here. R is equal to 1 with an angle of omega. So Z is equal to, the magnitude is a 1 and e power j omega with an angle. Is a complex Z plane, we are calling it as S plane and the Z plane. I will draw the S plane here. S plane. See, in the S plane, there is a ROC is a region of convergence. S is greater than A, S is less than A. Okay. S is greater than A means the region is in the positive. So mu of t, whenever there is a step function mu of t, the S is greater than A. The region of convergence is totally the greater than A in the positive side of the values. And S is less than A, it is a folded function of the step mu of minus t. And the negative sign is also for S is less than A. Means the negative real axis, the left hand side. For the stability, whenever if you go for the stability, we can find out the mapping of S plane to the, let us assume this is Z plane. When in the mapping of S plane and the Z plane, here S plane means the sigma is a real axis and the j omega is a imaginary axis. Since S is equal to sigma plus j omega and sigma is equal to 0, it becomes of a Fourier transform. And the Z transform is R is equal to 1. The magnitude is equal to 1 is on the unit circle. It becomes of the Fourier transformation, nothing but the discrete time for Fourier transform. There is a relation is there for Laplace transformation, Z transformation, and these two are related to the Fourier transformation also. Okay. Coming to the stability. all the poles that are present in the left half of the S plane means here all the poles that are present in the left half of the S plane. This will get in the control systems. They are typically students, they know the poles whatever we have. Poles means in the given equation, the denominator roots. Is there any numerator and the denominator we have? The numerator roots we can call it as a zeros, and denominator roots we can call it as a poles. The poles that are present in the left half of right half of the S plane, right half of the S plane, system is unstable. Any one pole, and the poles that are present in the left half of the S plane, left half of this plane, system is stable system. Poles, remember my dear students, the poles that are present in the left half of the S plane, the system is a stable system. Any one pole that is present in the right half of the S plane, the system is unstable system. And a pole that is present on the imaginary axis, we can call it as a marginally stable system or conditionally stable system. So three conditions we'll get. When we'll get it is imaginary, the quadratic expression, which are having the roots that we will get by using the minus b plus or minus square root of b square minus 4ac. Is there any complex roots we have? Or the complex roots in the poles that are present on the imaginary axis, then the system saying that is a marginally stable system. Okay, the left hand side and also the on the imaginary, we can call it as a stable, but it is a conditionally stable system. Conditionally stable system. If any one root that is present in the right half of the S plane, if any one root that is present in the right half of the S plane, the system is unstable. Coming to the Z plane, the mapping here. This is Z. Z is greater than A and the Z is less than A also. And Z is equal to A. These are the three conditions we have. Let it is Z is greater than R. Okay, A is nothing but you can take is a radius of here, the unit circle. Let this a unit circle 1 and minus 1. And this one is a minus 1j and this is a plus 1j. The circle around the with the radius of 1. Z is greater than A or Z is greater than R. Here showing that is with the radius R, and Z is less than R and Z is equal to R. So I am taking Z is greater than A means outside the circle. Outside the circle, total. This total outside the circle means here the greater than the minus 1, less than the minus 1, and greater than the 1 here, and this also the less than the minus 1 and the greater than the 1 imaginary axis, greater than outside the circle it is. Less than means inside the circle. Z is less than R because inside the circle, the radius is inside. Z is equal to means on the circle. Now the mapping here, the stability in the Z plane, is there any roots that are present in the left half of the S plane means the stability will get a stable system in the Z plane means the Z is less than the R. Inside the unit circle, the system is the digital system or the discrete system, discrete time Fourier transformation, the Z plane we can see here. In the equation of x of z, the poles that are present inside the unit circle. Inside the unit circle. Once again, I'm saying inside the unit circle. Here in between of a -1 to the 1 and plus j to the minus j. Inside the unit circle is a stable system mapping here. The left half of the S-plane, all the poles that are present in the left half of means stable system in the S-plane. And coming to the Z-plane, all the roots that are present inside the circle, then we can say stable system in the Z-plane. When it is as unstable, the system is unstable when the roots are present in the outside the circle. What is that circle? Unit circle. Unit circle. Unit means is a 1 here with 1 radius. In the Z-plane, when it is unstable, the roots that are present in the outside the circle, Z is greater than A. Outside the circle, system is unstable. Inside the circle, system is stable. Another thing is there here in the S-plane also. Marginally stable system is the mapping is on the circle here. On the circle. So Z is equal to R. In the Z plane, we can say it is a marginally stable system. Mapping with the S plane to the Z plane. Stable system in the S plane, analog functions. Stable system in the S plane in the analog system, that roots that are all the roots that are present in the poles, simply say. Poles and the zeros also, my dear students. Not only the poles and the zeros, all the roots that are present in the left half of the S plane, the system is stable. The mapping in the Z plane is all the roots that are present inside the circle, including the zeros and poles, my dear students. Once again, I am saying the previous slide said there is only the poles, the zeros and the poles. So the zeros is representing like this, and pole we can represent it as a cross mark. Okay. So unstable means any one pole that is present in the right half of the S plane, then that is unstable system, and in the Z plane, the Z is greater than ROC. And the marginally stable system is the poles that are present in the any one pole that is present on the imaginary axis, then we can say the system is marginally stable system, and it is mapping with the Z plane, it is on the circle. On the circle. This is stability in between of S plane and the Z plane, and the mapping also. Following, my dear students. Now coming here, in this unit circle, R is equal to 1 with an angle of omega, Z is equal to R into e power j omega, and R is 1 here. When R is not equal to 1, the Z transform is equivalent to, the Z transform is equivalent to, so I am substituting here the x of R of e power j omega, and Z is also R into e power 0. Write this as R power minus n, x of n, e power minus j omega. It is a Fourier transformation of a discrete time Fourier transformation. Discrete time Fourier transform, R power minus n, x of n. R power minus n, x of n minus 2. The Fourier transform of x of n actually whenever R is equal to 1. But now here it is R is not equal to 1. It is a Fourier transform of R power minus n and the x of n. Because it is e power minus j omega n. Is for the discrete minus, dear students. Remember here it is we are not using the x of t, and also it is not the integral, the sum of. Mostly when we are using the sum of means that is a discrete time functions only. Okay. Now take the one example here. Example. consider a signal x of n is equal to a power n mu of n. In the Laplace transformation also, we find out e power minus at mu of t. E power minus at mu of t. 1 by s minus a or s plus a. Got it, my dear students? It depends upon the e power minus and the plus. 1 by s minus a and 1 by s plus g. So the same thing, the discrete time function, if I am taking now as a power n mu of n, a power n mu of n, with a is in between of 0 to 1, 0 to 1, the z transform of x of n is, you can find out in substituting the definition of the z transform. So what is the definition of z transform here? X of z is equal to sum of n is equal to minus infinite to infinite, x of n z power minus n is the definition of the z transform. How to find out the z transform of the signal x of n is equal to a power n mu of n. Substitute here. Sum of n is equal to minus infinite to infinite. X of n is a power n mu of n, the given signal, and z power minus n. What is a mu of n? Nothing but the step function, but not in the continuous, but in the discrete. How you can represent the discrete function of mu of n? Graphical representation of mu of n is 1 at the 0 and 1 at the 1 also, and the 2 is also 1, 3 is also 1, and so on up to the infinite. But variable is n here. Okay, so sum of the remaining all functions is a 0 here. Minus 1 is a 0, minus 2 is also the 0 here. So we start from n is equal to 0 to infinite, a power n, keeping the mu of n is a 1, z power minus n, okay, is equal to sum of n is equal to 0 to infinite, a z, I'm taking here the minus 1 whole power n. So a power n, z power minus n. Now it looks like the sum of n is equal to n1 to n2 a power n. So what is the formula we have? The sum of n is equal to n1 to n2 a power n1 minus a power n2 plus 1 by 1 minus a. This is a formula we have. Instead of n1, here the 0 is there. So what is the a here? A power n is equal to, what is the a? Totally a into z power minus 1. So a z power minus 1 whole power n1. What is the n1 here? 0 minus a z power minus 1 whole power. What is the n2? Infinite. Infinite plus 1 is again the infinite one, by 1 minus a z power minus 1, because it's a 1 minus a. Anything power 0 is a 1, anything power infinite is a 0. So 1 by 1 minus a z inverse. X of z is equal to, we got x of z is equal to 1 by 1 minus a z inverse. Got it, my dear students? And now, in this condition, a is always less than the 1. A is always less than the 1. Whenever you can use this formula, a is less than the 1. Otherwise, you will get the negative value. So, what is the a here? A z power minus 1 is less than 1. And z power minus 1 means a by z is less than 1. And a is less than the z, but z is greater than A is ROC. Z is greater than A. Is ROC is outside the circle. See, the A is the dotted lines showing here and the shaded here. The shaded, whatever the shaded area is there, that is ROC for A power n mu of n. A power n mu of n. Z is greater than A is the ROC for x of n is equal to A power n mu of n. Remember here, my students, mu of n in the Laplace transformation is right-sided. In the Z transformation is outside-sided. Outside the circle, Z is greater than A. The total outside the circle. Here the shaded area is there, the gray color. For A power n mu of n, the Z transformation is 1 by 1 minus A Z inverse, using this condition here. And also n2 is greater than n1, definitely. And these two conditions satisfied, and only can use this formula. The sum of n is equal to n1 to n2 A power n is, here n2 is always greater than the n1, and A is always less than the 1. So using this relation, A is less than 1, I took A z power minus 1 is less than 1, A by z is less than 1, A is less than the z, and z is greater than A. Got it, my dear student? Z is greater than A is the region of convergence. With the region of convergence being the set of Z such that Z is greater than a pole zero plot. You can see, my dear students, pole zero plot. So denominators we can call it as a pole. So pole we can represent it as a cross mark, and zero represented as 0. If any 0 is there, we can represent it like this. So that is in the numerator. Zeros are the roots in the numerator given function, and the denominator roots we can call it as a poles. So pole zero plot and ROC of the example A power n mu of n. Got it, my dear students? And now coming to the second example here, it's very, very important. These two are very important because for both the functions, the Z transform is same. 1 by 1 minus A Z inverse only. The difference is the region of convergence. Previously, the region of convergence is outside the circle, the unit circle, and here inside the unit circle. Inside the unit circle. Now, you see, the given signal is minus A power n minus A power n mu of minus n minus 1. Minus n mu of minus n minus 1. So in the definition, x of z is equal to the sum of n is equal to minus infinite to infinite x of n z power minus n. The definition of Z transformation. How to find out the Z transformation of the signal x of n is equal to sum of n is equal to minus infinite to infinite. The given x of n is minus A power n mu of minus n minus 1 z power minus n. Okay, this is a given signal. Now we can change these limitations. Change the limitations mu of minus n minus 1. Mu of minus n minus 1, my dear students, is minus means the negative real axis. So let us see the mu of n graphical representation starts from the 0 is a 1, 1 is a 1, 2 is also 1, and 3 is also 1. Okay, what is a mu of minus n? Minus means is a folded at the 0. There is no any change in the 0, the value is 1. And now 1 will get in the minus 1, is also magnitude 1. Minus 2 is now is a 1. Minus 3 is a 1. And 1, 2, 3 is a zeros. Mu of minus n. And this mu of minus n, mu of minus n, now I am subtracting mu of minus 1. Subtracting the mu of minus 1. So folded function, the folded function or mu of, take the minus as a common here. Take the minus as a common, mu of minus of n plus 1. Plus means is advanced function. But you have to do for the folded function. One sample is moves towards the left hand side. One sample moves towards the left hand side. Got it, my dear students? If any can add for the folded function, it can move towards the right hand side. But the subtraction in the folded function means the left hand side. Okay, minus means the delay. But mu of n is there, you can shift towards the right side. Mu of n is there, you can shift towards the left side plus 1. But the folded function, reverse operation. Or you can use this, the mu of minus of n plus 1. Plus you can remember it is an advanced function towards the left side. But for the folded function, okay, folded function is one sample towards the left side. So 0 is now the 0. And start from the minus 1 is a 1. Minus 2 is a 1. And minus 3 is a 1. And so on. So from minus infinite to 2. And here also the so on. So mu of minus n minus 1 value is a 1 with a range of n is equal to from minus infinite to minus 1. Remember my students here. Minus 1. Okay. Don't write it as a 0. Because it's shifted towards the left side with one sample. Minus a power n. And this value is a 1. After changing these limitations. Z power minus n. Okay. Now I am changing the sum of minus is already there. Here the minus n is equal to, you can add 1 to infinite or the infinite to 1 is both are the same. So minus 1 to minus infinite. A z power minus 1 whole power n. So now you can remember here, my students, if you change these negative signs in the summation, you can keep the negative power. Got it, my students? Is equal to minus sum of n is equal to 1 to infinite. Changing both the negatives is positive and keep here z power minus 1 whole power minus n. It's a very important one. Now, I'm doing this one. You see, when it is in the form of a power n only, the sum of n is equal to n1, n2, a power n is equal to a power n1 minus a power n2 plus 1 by 1 minus a, and n2 is always greater than n1 and a is less than 1. We know this condition is a very important formula. It is a power n only, the positive value. So I'm changing this x of z is equal to minus, already we have sum of n is equal to 1 to infinite, including that it is a minus inside. So a power minus 1 and the z whole power n. So whenever if I am taking the minus inside, the minus a power minus 1. Minus into minus is a plus and it is positive. Now it looks like sum of n is equal to n1 to n2 a power n. What is the n1 now? n1 is a 1. So a power minus 1 into z whole power 1 minus and a power minus 1 z whole power infinite plus 1, because it is a upper limit is infinite only, by 1 minus a inverse z. And already we have the minus is there in front of that minus. So anything power 1, this value will get the same. Infinite, anything power infinite is a 0. Okay, minus of, what is the value here? A power minus 1 into z whole divided by 1 minus a inverse z. According to this condition here, a is less than 1. What is the a here? A inverse z. I am taking the a inverse z is less than 1, z by a is less than 1, and z is less than a. What is ROC now? Z is less than a. Remember that one. And simplify this. Take the a inverse z is a common, minus a inverse z is same, take the common, a inverse z whole divided by 1 by a inverse z minus 1. Got it, my dear students? I'm taking the denominator as a inverse z as a common, a inverse z as a common, 1 by a inverse z minus 1. So a inverse z and a inverse z is a get cancel, and it is equal to 1 by a inverse z. 1 by a inverse z means you can bring that in the numerator. A inverse in the numerator is a, z is in between the numerator is a z inverse minus 1. Already in front there is a minus is there. Multiply this minus 1 by 1 minus a z inverse. 1 by 1 minus a z inverse. So the same response we'll get for the minus a power n mu of minus n minus 1 also. Got it, my dear students? The same thing for a power n mu of n, this is a transformation you can apply. It is the same, 1 by a z inverse. And for the same minus a power n mu of minus n minus 1 also, the z transformation will get the same thing, 1 by 1 minus a z inverse. But ROC is a difference. What is ROC for this one? ROC is z is greater than a. Remember this one. Okay, ROC for a power n mu of a. And z is less than a, ROC for minus a power n mu of minus n minus 1. Okay, to find the inverse z transformation for the given 1 by 1 minus a z inverse, it depends upon the ROC, the inverse z transformation is changes. If ROC is greater than means, we can write as a power n mu of n. If ROC is less than a, we can write as minus a power n mu of minus n minus 1. Got it, my dear students? So see here the same thing, they also did x of z is equal to minus sum of n is equal to minus infinite a power n mu of minus n minus 1 z power minus. And taking the limitations here from minus infinite to minus 1, replacing the mu of minus n minus 1 is a 1, so e power n z power minus n. And minus v already there. I'm changing these signs as positive values and change the powers as a positive to negative and negative to positive. So here the positive is there, write it as a negative, and here the negative is there, and you can write as a positive. So why they wrote this 1 minus means 1 minus, because it starts from the 1, n is equal to 1. Okay, when you can substitute n is equal to 0 here, n is equal to 0 also, a power 0 and a power z power 0. Anything power 0 is a value is a 1. You can subtract from 1 minus minus. Or otherwise, directly using this one, you can substitute in the whatever the formula we already know. 1 by 1 minus a. After simplification, you will get 1 by 1 minus a z inverse. With the ROC being the set z is such that z is less than a. Note that the Z transform is same as that of example 1. The only difference is the ROC. In fact, example 2 is just a left-sided version of example 1. Right-sided means mu of n. Left-sided means mu of minus n and minus 1. Why it is not minus 1? We can ask the question like this also. But actually, mu of n starts from the 0. Okay, is a positive, including the 0 also, it is a positive. So I'm not taking the 0 because it is a discrete time function. You can take from minus 1, minus 2, and minus 3, minus 2. But in the continuous time function, there is a in between minus 1 and the 0 is also the values is there. So for that condition, they are taking there, it is a mu of n and the mu of minus n for continuous time function. And coming to the discrete time function, left-sided means mu of minus n minus 1. Right-sided means mu of n. Left-sided version of example 1. What it is? Example 2. Got it, my dear students? It's a very, very important examples, a power n mu of n and minus a power n mu of minus n minus 1. Okay. Next one. And here the whole 0 is there. So first of all, I shown outside the circle, the shaded area here in the gray color. Outside the circle, A. Now, and this the shaded area is inside, there is a gray color because it is Z is greater than, Z is not the greater than, less than. Z is less than, A is ROC inside the circle. Stable system. Previously, it is outside the circle. The shaded area is outside the circle. Unstable system greater than A. Got it? ROC. The pole 0 plot of ROC of example 2. Okay. So coming to the third example here. Third example, my dear students. Consider the signal. Consider the signal. X of n is equal to 7 1 by 3 whole power n mu of n minus 6 1 by 2 whole power n mu of n. Okay. 7 is a constant, 6 is a constant. Now it is in the form of a power n mu of n and a power n mu of n. Directly can write. So what is a power n mu of n? The transformation is, what is the Z transformation? 1 by 1 minus a Z inverse. What is the a here? 1 by 3. What is the a here? 1 by 3. So the transformation of the given signal x of z is equal to, using this a power n mu of n, I'm directly writing here the 7 is a constant. 1 by 3 means 1 by 1 minus 1 by 3 z inverse. Okay, this a power n mu of n minus 6 is a constant, multiplication factor, a power n mu of n. What is the a here? 1 by 2. So 1 minus 1 by 2 z power minus 1. Okay, z power minus 1. Now we can simplify this one. X of z is equal to, x of z is equal to, you can write as 3z minus 1. So z power minus 1 means it's also denominator only. Okay, Or directly here there is a 7 into 1 by 1 minus 3 z inverse minus 6 into 1 by 1 minus 2 z inverse. The final answer it is. But it matters. Or you can simplify the 7 by 1 minus 1 by 3z minus 6 by 1 minus 1 by 2z, okay, is equal to, you can bring that in the numerator, 7 3 is 21z whole divided by, take the LCM here, 3z minus 1 minus 6 2 is 12z whole divided by 2z minus 1. Still you can go for the simplification by taking the LCM of 3z minus 1, 2z minus 1 and multiply and simplify. Okay. Or directly you can keep like this only, simply x of z is equal to 7 into 1 by 1 minus 1 by 3 z inverse minus 6 into 1 by 1 minus 1 by 2 z inverse. Got it? So now the ROC. So what is the ROC here? Previously see the given functions, these also the a power n and it is also a power n. Z is greater than, for this function z is greater than 1 by 3, and for this function the z is greater than 1 by 2. Here the minus is there. Okay. Now the ROC you can see for x of z to converge, both sums in x of z must converge. So we need both z is greater than 1 by 2 and z is greater than 1 by 3 and 1 by 2. Thus, the ROC is a set of z such that z is greater than 1 by 2. Why is this z is greater than 1 by 2? It is greater than the 1 by 3 and greater than the 1 by 2. So 1 by 3 and the 1 by 2. 1 by 2 means is a 0.5. 1 by 3 means is around third one. So 1/3 and here the half one. So this value is greater than, and from 1 by 3 is less than the value compared to the 1 by 2. So thus the ROC is the set of z such that z is greater than 1 by 2. Z is greater than 1 by 2 only. The pole and the zero, full zero plot of ROC of the example. So I will show here. The ROC we can take here. Z is, if I am writing it as a z is 1 by 3 here. 1 by 3. So 1 by 3 means a point 0.3 around, and this one is a 0.5333 something. Z is greater than outside the circle here. Outside the circle, the first one. Z is greater than 1 by 3. Okay. Now I'm checking the another circle here. This is another circle. What is ROC here? The ROC now 1 by 2. Means outside the circle is greater than, outside the circle. So outside the circle. So what is a common ROC now? Common ROC. If it is greater than 1 by 3, there is no any overlapping here of both the ranges. But in the when the greater than 1 by 2, there is a overlapping occurs for the greater than 1 by 3 and the greater than 1 by 2. Okay. So what is ROC? Thus the ROC is a set of, see the shaded area here. But I am not taking the 1 by 3. So outside the 1 by 2 only. Okay. Thus ROC is a set of z such that z is greater than 1 by 2 because there is a overlapping. But z is greater than 1 by 3 and z is greater than 1 by 2. When we take the from z is greater than the 1 by 3 here, but there is no any overlapping of z is greater than 1 by 2. So combine ROC you have to write, because the given function is the additive combination of the two functions. Understood, my dear students? Okay. Now, the properties of ROC, the properties of Z transformation is also there. Now the properties of ROC, remember and listen carefully, my dear students, because in the part A, you have to write the part A, there is some questions, and the part B, you have to write some questions. Definitely, these are the properties of ROC of Z transformation, and the properties of ROC of a Laplace transformation is a 3D question. Directly, you have to write some points. You'll get the 3 or 4 marks. It's very important. No need to prove the ROCs when they given in the part A. If suppose they given in the part B, means you have to prove the ROCs also, the region of convergence. So first property saying that the ROC is a ring or disk. Unit circle. ROC is a ring or disk in the Z plane, center at the origin. See, is a Z plane, we can take that R is a radius, we can draw a radius with the center with origin, the unit circle. Okay, the ROC is a ring or a disk in the Z plane, center at the origin. It is a 1 or 1 by 2, it depends upon the value. So actually we are taking always the default, the unit circle. Okay, and property 2 saying that discrete time Fourier transform of x of n. Discrete time Fourier transform of x of n exists if and only if ROC includes the unit circle. ROC includes the unit circle. When R is equal to 1 only, then the transform becomes a Fourier transform. That too, discrete time Fourier transform. Discrete time Fourier transform of x of n exists if and only if the ROC includes the unit circle. By the definition, ROC is a set of Z such that x of Z converges. Discrete time Fourier transform is the Z transform evaluated on the unit circle. Why I am saying this, already we seen the x of R into Z power, not the Z, e power j omega is equal to the sum of n is equal to minus infinite to infinite, x of n, Z is nothing but R into e power j omega whole power minus n. When R is equal to 1, nothing but the unit circle is a unit circle, or we can call it as a disk also. Okay, it becomes of x of e power j omega is equal to sum of n is equal to minus infinite to infinite, x of n e power minus j omega is the definition of Fourier transformation for discrete function, sum of. So we can call it as a discrete time Fourier transformation is evaluated on the unit circle. Therefore, the ROC includes the unit circle, then the x of Z converges for any value of Z on the unit circle, that is discrete time Fourier transform converges. Got it, my dear students? This is the second property of ROC. And third property, the ROC contains no poles. ROC is the region of convergence. Region of convergence is greater than the R and the less than the R and equal to R. The region of convergence contains no poles. Fourth property saying that if x of t is a finite impulse response, remember my dear students, FIR filter, we can call it as, then ROC is entire Z plane. Entire Z plane means from below the minus infinite and the below the plus infinite. This total shaded area, entire the Z plane. When in the finite impulse response, FIR, if x of n is a finite impulse response, then the ROC is entire Z plane. Not inside, outside like this we are saying, entire Z plane. Below the minus infinite and below the plus infinite and below the plus J infinite and minus J infinite. It is not equal to, always in the boundary, inside the boundary. The fourth property saying that. What is the fifth property? If x of n is a right-sided sequence, right-sided means outside the circle. I already told the S plane and the Z plane. Right-sided is outside, left-sided is the inside, and on the imaginary, on the circle. The mapping here. The fifth property saying the same thing. If x of n is a right-sided sequence, then the ROC extends outward from the outermost pole. Outward from the outermost pole, right-sided. Okay. If x of n is a left-sided sequence, see here, this one the left-sided. This is a left-sided. This one is a right-sided. Right-sided means outside of the outer world from the outermost pole. If x of n is a left-sided means stable system. The ROC extends inward from the innermost pole. Inward, this is the inward here. My dear students, inward of the Z plane. Okay. The left-sided sequence, if x of n is a left-sided sequence, then the ROC extends inward from the innermost pole. If x of n is a right-sided sequence, the ROC is outward from the outermost pole. Okay. If x of n is a finite impulse response, then the ROC is entire Z plane. Entire Z plane. These are the fourth, fifth, and the sixth properties. First property saying that the ROC is a ring or a disk in the Z plane, is centered at the origin. And the second property saying that discrete time Fourier transform of x of n exists when it is exits on the unit circle, because r is equal to 1. The z is equal to r into e power j omega. R is a magnitude and omega is a phase angle. Then r is equal to 1, nothing but the unit circle. The discrete time Fourier transform of x of n exists if and only if the ROC includes the unit circle. And third property saying that ROC contains no poles. The region of convergence, outside, inside, and the on. And fourth property saying that the entire Z plane is ROC, means x of n is a finite impulse response. And the ROC is only the outward from the outermost pole, means the x of n is a right-sided sequence. And the sixth property saying that ROC extends inward from the innermost pole, means the left-sided sequence. Got it, my dear students? Remember these all the 6 properties. Definitely you'll get in the part A, the as with the 4 marks. You can write any of these 4. And some more is also there, the properties. 7th property saying here, if x of z is rational, x of z is equal to, the numerator is a of s, a of z, and denominator we have considered as a b of z, where a of z and the b of z are polynomials, quadratic expressions. And if x of n is a right-sided sequence, then the ROC is a region outside the outermost pole. If x of n is the right-sided, even in the given function x of z is a rational, in the form of A of z and the B of z, where A of z and the B of z are polynomials, and if x of n is right-sided, then the ROC is the region outside the outermost pole. Let us say here the x of z is equal to A of z by B of z. A of z as a sum of A suffix k z power k, and Bz can represent it as a pi poles 1 minus P suffix k z power minus 1, P suffix k power minus 1 and z whole power k. And simplify this, we'll get z is greater than the P1, and the other is the right side because x of n is a right-sided. 1 by 1 minus 1 by 3 z inverse, 1 by 1 minus 1 by 2 z inverse. For example, if it is a function, we have not understood this one, function, the z is greater than the 1 by 2 because in the two poles, 1 by 3 and the 1 by 2, see the causal and stable and the causal and unstable and the non-causal. I already explained this one, it's a 10th property. And each of the term in the partial fraction has an ROC being a set of z such that z is greater than the pi. Why it is a pi means the 1 by 2 only. See the pi here, ci by the pi poles, that is always greater than the pi, not the c suffix I. Each term in the partial fraction has an ROC being a set of z such that z is greater than the pi because x of n is a right-sided. In order to have x of z is convergent, the ROC must be the intersection of all individual ROCs. Therefore, ROC is taken outside the outermost pole. Outside the outermost pole means 1 by 3 is less than the 1 by 2. So you can take the outermost pole only, the 1 by 2. Then the ROC is the region the z is greater than the 1 by 2. Got it, my dear students? Okay. If any functions like this, the rational function, in this rational function, the B of S having the poles, in that pole also, z is greater than the pi. That pi is, you can take the ROC is, which is outermost pole. And ninth property is saying that a discrete time, linear time invariant system is stable if and only if the ROC of h of z includes a unit circle. H of z includes the unit circle, means inside the system. The system is stable if and only if h of n is absolutely summable, if and only if the discrete time Fourier transform of h of n exists. Consequently, the property 2, ROC of h of z must include the unit circle. Stable system. So I already told causal and stable. Causal and stable means, see here the poles that are present inside the circle, stable system. See, unstable means any one pole that is outside the circle. So I am taking the unit circle here, the pole is outside the circle here, unstable system. And non-causal and stable. Non-causal and stable means one pole is also in the outside the circle. See, this of the circle is there. The poles that are present inside this circle, causal and stable. The poles that are present inside the circle, and if any one pole is outside the circle, is a non-causal and stable. And see here, inside and the outside is also there, unstable system, the region of convergence. So in between the shaded area here, see, the shaded area is outside the circle, and shaded area is outside the circle ROC, and shaded area is in between the circles, A causal discrete time linear time invariant system is stable. A causal discrete time linear time invariant system is stable if and only if all of its poles are inside the unit circle. All of its poles. When it is a stable, my students, all of its poles are inside the unit circle. Inside the unit circle, then we can call it as a stable system. Causal and non-causal. If any is outside the circle, means unstable system. Got it? So with this, the introduction of Z transformation and with some two examples, the definition of Z transform and the discrete time Fourier transformation relation with Z transformation, and how we can plot the pole zero plot to find the ROC the outside the circle here. And with this example, the ROC is inside the circle, the shaded area. And third example showing that the ROC can take the outermost pole because the overlapping occurs for innermost and outermost is a overlapping area. And 10 properties. The properties is related to the region of convergence. Okay, 10 properties. No need of the proofs, my dear students. Here you can learn only the what are the ROCs, property 1 to the property 10. Okay, so any doubts? The tomorrow class we can start the properties of Z transformation. Here the properties of ROC related to the Z transform. Now we can, tomorrow's class we can discuss about the properties of Z transform. Any doubt? Okay, thank you.